Okay, so we're going to go ahead and we're going to move into section 9.2, and we're going to look at our actual significance tests and how do we run them. So like our confidence intervals, we're going to have some conditions that must be met for our one sample z-test. And so the first one is that it has to be random. Our data must come from a well-designed, simple random sample or randomized experiment. Other words, the information we have cannot infer to the population or cannot establish cause and effect. So cause and effect comes from our experiment. Inferring to the population means that we've had a really well-designed random sample. Next thing is that our distribution, our sampling distribution needs to be normal. It needs to be approximately normal. So the normal condition for proportions is typically successes has to be greater than 10 and failures have to be greater than 10. And if we don't know successes and failures, then we just take our sample size times by our proportion, and that has to be greater than or equal to 10. And then our sample size times 1 minus our proportion has to be greater than 10. Now we're going to see something a little different here, because now all of a sudden, instead of using a proportion from our sample, we're going to use the proportion from our null hypothesis, our PO. So now this is going to change into n times PO has to be greater than or equal to 10. So that comes from our null hypothesis. And then n times 1 minus PO has to be greater than or equal to 10. So again, coming from our null hypothesis, we're going to use that proportion value, not the proportion from our sample. And then of course we have our independence clause, where either they are truly independent from each other, or if we're sampling without replacement, we have to meet that 10% condition. So going back to our very first problem, we had this person who believed that they made 80% of their free throw shots. They're bragging, oh, I'm an 80% free throw shooter, blah, blah, blah. And then it comes around that when we actually had them shoot 50 free throws, they only actually made 32 out of the 50. So now we're checking, are they really an 80% free throw shooter, or are they less than an 80% free throw shooter? So we check our conditions, random. Because this was an experiment and each free throw shot we're assuming is independent of each other, making one does not affect if you make the next. Independence of shots makes the sample random. So we took a selection of 50 shots, and then we're going to check to see if it's normal. So 50 shots he took, and we're assuming 80% of them should be made. That gives us 40, equals 40, which is greater than or equal to 10. And then 50 times our remaining 20%, which is 10, should be greater than or equal to 10. And so because of the or equal to, we're good. We meet our normal condition. And of course, that independence, one shot should not affect another shot. And if you took sports psychology, you could probably debate that until the cows come home. But ideally, one shot should not affect another. If you make one, it should not affect if you make the next one. So calculations. So we check our conditions. Now we're ready to go to calculations. And we do two different types of calculations. We calculate a test statistic, which is really just a z-score. It's our standardized score. And then we calculate the probability value. What's the probability of getting that value? And so significance test uses our sample data to measure the strength of the evidence against HO. And here are some principles that apply to most tests. The test compares the statistic calculated from the sample with the value of the parameter stated in the null hypothesis. And so we're going to see how far away that is from the value in our null hypothesis. And we're going to go ahead and we're going to check the direction specified by our alternative hypothesis for evidence against our null hypothesis. So really, we're just going to assess how far away the statistic is from the parameter by standardizing the score and then checking the probability of that by our normal distribution. So our test statistic we're calculating is also known as Z, or a Z-score, where we take our statistic minus the parameter and we divide by, and this is actually incorrect, the standard deviation of the parameter of our PO. And so as we calculate it, this is the only thing that's coming from our sample. Everything else is coming from our null hypothesis. So this is coming from our null, this is coming from our null, because everything is based on the idea that the null hypothesis is true. And if the null hypothesis is true, what's the likelihood of getting a sample like we did? And if it's so rare to get a sample like we did, then the null hypothesis then is probably not true. And that's the whole idea behind our test. Now, once we calculate our Z-score, we then calculate the probability of getting that value. And so now we're going to start calculating those p-value, which is just a probability value, the probability of getting that result by chance. And that means we're going to start using normal CDFs. And we're going to use a normal CDF for a Z-score, which means we're going to have a mean of 0 and a standard deviation of 1 on our CDFs. So, sample problem: a basketball player claims to make 80% of the free throws he attempts. We think he might be exaggerating. To test this claim, we'll ask him to shoot some free throws. In a simple random sample of 50 free throws, the player made 32 of the free throws. So our null hypothesis is he claims that he's an 80% free throw shooter. We think that he's not. And so our PO is going to be 0.8, but from our sample, we get a p hat of 32 out of 50, which is 0.64. So now we're going to calculate our test statistic. So our test statistic, or our Z, which is really just our Z-score, is going to be our statistic minus our PO from our null hypothesis, and then we're going to calculate the standard deviation of this. So the 0.8 times 0.2 divided by our sample size. So this is the standard deviation of the sampling distribution based on the null hypothesis. And so this is going to give us a value of negative 0.16 over 0.0566. And when I divide, I get negative 2.8284. So what does this mean? Well, when I look at my p-value, or my distribution, it's a standardized distribution, so it's going to be centered at 0. We're going to have standard deviations of 1, 2, 3, 4, negative 1, negative 2. And we think we have a z-score of negative 2.8. So we're down here, and then we're looking at the probability that it's less than that. So we're looking at this probability right here, and it looks really small. So we're going to go ahead and calculate that. Normal CDF. Our lowest value is really low, and we're going to play it safe here by saying our lower bound is negative 10. And here our upper bound should be our z-score, negative 2.8284. Our mean should be 0 because, again, it's a standard normal curve, and our standard deviation should be 1. And so we calculate that out, and we found the probability that our z is less than negative 2.8284. This probability becomes 0.00234. Now, why did I write it like this? Why did I write the probability of this? Because this is a notation that you're going to see every once in a while, and I want you to be familiar with what it's saying. So the probability that I get a z-score that is less than this z-score that I got is really, really small. So given that the null hypothesis is true, the probability that that guy would shoot that bad at free throws is a 0.2% chance, which is really, really small, and it's really rare. So that's convincing evidence that he was lying. He is not an 80% free throw shooter. And so please know that the p-value from a simulation and a p-value calculated by using the normal distribution are just estimates of the true p-value. Because again, we're always just kind of estimating to the best of our abilities. And so this is a really good estimate of him doing this just by chance, or shooting that bad by chance. Now, keep in mind, this is not a 0% chance. It's very low, but there is a possibility, as small as it could be, that he could just shoot that bad by chance. Okay, so our 4-step process, so this is in your notes for you. We've got our state, what hypothesis do you want to test, what significance level. You have to state these. If you do not state these and you do not state the significance level, if you do not tell me what P stands for, you will not receive full credit. So those are really important. With your plan, name the procedure you are using. We're using a 1-sample z-test for proportions. So last time we were using confidence intervals, so it would be a 1-sample z-interval for proportions. Now we're doing a significance test. We have our random condition, our normal condition, our independence. We compute p hat before we go too far. We compute our test statistic, which is calculated by this. And then we find our p-value, which we'll find with a normal CDF. And something I want to point out about that normal CDF is if your HA has a P is less than PO, then your lower bound is going to be -10, and your upper bound is going to be your Z. So whatever value you got for Z. If your HA is P is greater than PO, then your lower bound is going to be your Z, and your upper bound is going to be really high, like 10. Now, if your HA is what we call a two-sided test, you couldn't decide if it was going to be higher or lower, so you just said P is not equal to PO. You're going to do a 2 normal CDF, because you're going to have 2 tails, one on each side, a greater than and a lower than. And then you're going to do one of them. You're going to do either the less than or the greater than, depending on your Z value. So if your Z value is positive, you're going to do the greater than. If your Z value is negative, you're going to do the less than version of that. And then we, of course, we interpret our results, which is probably one of the most important things. And since our p-value, so we're always comparing that to our significance level. If our p-value is, since our p-value is greater than our significance level, no, since our p-value is not, we want this to be colored, here we go, not greater than our significance level alpha, we fail to reject. So if it's not lower than, then we fail to reject, and we do not have sufficient evidence. If our p-value is less than our significance level alpha, we reject HO, and so there we do have convincing evidence, or we do have sufficient evidence. Again, always saying our HA in context. So when we interpret, we're always interpreting in terms of HA, and when we reject or fail to reject, we always say that's in terms of HO. And the more you practice it, the better you get. So what happens when the data does not support your HA? So let's say you say, okay, P is 0.8, and I really think that he is less than an 80% free throw shooter, and then all of a sudden he shoots 53 free throws, and he makes 49 out of 50. That 49 out of 50 does not support your HA, so you just stop. There's no need to continue with your significance test, because right now your conclusion is clear. You fail to reject HO because your evidence does not support that it is less than 80%. So if you're not careful and you don't pay attention, you're going to go through all the motions of the test and you're going to come up with the same conclusion that you should have had just from paying attention, that your data did not support your alternative hypothesis. And so it's just a lot more work for the same answer because you didn't really pay attention to what you were doing. Okay, so our first problem that we're going to try on shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate this, a random sample of 600 American Idol fans is selected. Okay. And they are shown the audition tapes of 12 never seen before contestants. For each fan, the order of the 12 videos is randomly determined. Thus, if the order of performance doesn't matter, we would expect approximately 1 out of 12 fans to prefer the last contestant they view. In this study, 59 of the 600 fans preferred the last contestant they viewed. Does this data provide convincing evidence that there is an advantage to going last? So we're going to test the hypothesis that the true proportion of American Idol fans prefer last performer is 1/12. I don't know what that is as a fraction yet, but we'll calculate that later. If you don't know what significance level to use, we use 0.05 just as kind of a safety because that's what's used in the court of law. So our null hypothesis is that there should be no difference. So we suspect that, or we hope there's no difference. They don't prefer the last performer, so the P should be 1 out of 12, which is, for convenience sake, 0.0833. But we think they actually do prefer the last performer. So we think that it's going to be greater than that value. So now we have to state, what does P mean for our null hypothesis? The proportion of American Idol fans that prefer the last performer. So don't ever forget to state what P means or what the mean is and all of that in context. So if conditions are met, we will perform a one sample z-test for proportions. I'm going to put for P because P stands for proportion. Random. We had a simple random sample of 600 American Idol fans. Normal. So 600 times 1/12 gives us 50, which is greater than or equal to 10. And then 60 times 11 out of 12, what's left over, gives us 550, which is greater than or equal to 10. So we've met our normal condition, we've met our random condition independent. It is reasonable to assume that there are more than, let's see, 600 in our sample, so 600 times 10 is 6,000 American Idol fans. How do we know this? Because millions used to watch back in the day. I don't know how many watch now because I don't pay attention, but. Okay, do. So the first thing we need to calculate is what is P hat. So P hat is 59 out of 600, which gives us a value of 0.0983. So now we're going to calculate our statistic, Z. So our actual statistic minus our p-value over our standard deviation of our p-value, 0.833 times 0.9167, sample size of 600. So this gives us 0.015 over 0.01128, which gives us a z-value of 1.3298. Now we have the z-value. Now we're ready to calculate the probability that z is, let's see, greater than, because that was our alternative hypothesis, than this value. So this will be a normal CDF. Because I want it greater than, my lower bound is the 1.3298. Upper bound is 10. Mean is 0. Standard deviation is 1. And that gives us a probability of 0.09179, which is not less than our significance level of 0.05, which means that we failed to reject because we failed that test. Helps if I spell reject correctly. Okay, since the p-value is not less than 0.05, we fail to reject. HO, which means we do not have convincing evidence of our alternative hypothesis. We do not have convincing evidence that American Idol fans prefer The Last Performer. So there's no convincing evidence. Okay, so next one is now how can you do it all on the calculator without help? So I show you how to do it step by step because a lot of times they want to see it broken down step by step, and multiple choice questions will ask for you. And even if you do it all on your calculator, you still have to show the formulas and how it's all set up. But this is a good way to check your answer. So there is a one proportion z-test on your calculator. So we're going to go ahead and look at that really quick. And so there we go. It's hard to see because, so there's my calculator, and if I click on stat and arrow over to test, we have all sorts of tests. We don't want to do just the z-test or the t-test. We're looking for a one prop because our z-tests for proportions are different than our z-tests for means. So I'm going to do a one prop z-test, and then you put in the information you need. So in our sample problem, we have a 0.2 PO, and then our sample has 63 out of 250 students, and our our alternative hypothesis is P is greater than that 0.02. So we can calculate, and it's going to spit out this information. And what you really need to know is here's our z-score, so we can compare that with the z-score we calculate. And here is our p-value, our probability value. And it even tells you your p-hat and your sample size, so you can double check that. And so now we're going to go ahead and look at the problem itself. So when we look at it, let's see, according to the National Campaign to Prevent Teen and Unplanned Pregnancy, 20% of teens aged 13 to 19 say they have electronically sent or posted sexually suggestive images of themselves. The counselor at a large high school worries that the actual figure may be higher at her school. So to find out, she gives an anonymous survey to a random sample of 250 of the school's 2,800 students. All 250 respond, and 63 admit to sending or posting sexual images. Carried out the significance test at the 0.05 significant level. What conclusions should the counselor draw? So we're going to test the hypothesis of the true proportion of teens aged 13 to 19 that have electronically sexted is 0.2. So we're going to assume that it's the same as the national average, 0.2, but she thinks it may actually be higher, where P is the proportion of students who are sexting. We'll perform a one-sided z-test for proportions. So is it random? Yep, there's a simple random sample of 250 students. So keep in mind, even though we can calculate a lot of stuff in the calculator, it doesn't check our conditions for us. That is still something we have to do. Normal, 0.2 times 250 gives us 50, which is greater than or equal to 10. So we're good there. And then 0.8 times 250 gives us 200, which is greater than or equal to 10. So we're good for a normal condition. Independent, we know that there are more than 250 times 10 students. In fact, they told us there's 2,800 students, so we're good. So we do know that. Do. So here, a lot of times if you're going to use your calculator, you can you can write off to the side a one prop z-test. You can write that PO equals 0.2, that X equals 63, that N equals 250, and that you had P greater than PO, because that's what we had right here. And then you can say what it gives you, but you still have to set stuff up. So you still have to tell me that my P hat is, what did that calculator say? P hat was 0.252. 0.252 minus our 0.2 all over the square root of 0.2 times 0.8 divided by 250. And you can check your calculation with what the calculator gave us. So the calculator gave us a z-score of 0.205548, and you can check with there. And so that's why it's nice having that test to check out, but you still have to write down this stuff. Our p-value ended up being 0.0199, which is less than 0.05. So we can reject our null because it is less than. So since the p-value is less than 0.05, we reject our null hypothesis. There is convincing evidence that to conclude that more than 20% of the teens at the school have sent sexually explicit photos of themselves. So maybe we should have a little thing to talk to them about the legality of that and all that sort of stuff like we're going to have here. So that's it for now, and we'll talk more about going over these z-tests.